All right, let's talk about the statistical graphic known as the histogram. Here's an example of a histogram, and typically histograms plot a single variable, but it's possible for them to plot multiple variables. For example, here the blue histogram would be for one variable and the purple would be for a second. And since they're overlaid, this would let us kind of compare these two variables. So they're usually one variable and they're always continuous data. So histograms display continuous variables. Remember from our table 1 section, we talked about summary measures of continuous variables that can help you understand the sample population. And just in the previous section, I talked about the best practices for statistical graphics and how one of them is to reveal the structure of the data, and how these summary measures alone don't reveal that structure as well as a plot. So the histogram is really well suited for revealing that structure of the data or the distribution of the data. Another word for that is the shape of the data. Basically, it gives a better idea of what that data really look like. So the horizontal axis, or the x-axis, is the variable's value on a histogram. And then the y-axis, or the vertical axis, is going to be the frequency of that for each given value. And a histogram basically works by binning the continuous variable and then plotting the frequency of each bin. So because a continuous variable might have many, many points between the bins, it basically will choose a start and end point for a bin and then count how many participants fall within that start and end point and then plot them. So the bar will be higher if there are more participants that fall into that bin or that have the values between the start and end of the bin for that given variable. All right, so let's discuss some possible distributions that you might encounter in the medical literature. The most commonly seen one is known as a symmetric distribution. And so in this case, the distribution is centered around a certain value, and it looks the same on either side. So just looking at this graph, we can deduce that values are just as likely to occur on one side of the average as the other. And this specific example here is both symmetric and unimodal. And so unimodal means that there's just one peak in the data. So the mode is defined as the most frequent value of a variable. And using this histogram, you can identify the mode as the highest peak. So in a symmetric unimodal distribution like the one we see here, the mean or the average, the median, and the mode are all going to be the same. They're all going to be right at that peak. And the normal distribution is a really commonly spoken about distribution that is symmetric and unimodal. That's when you'll see a good amount in the literature. It's a specific type of symmetric unimodal distribution. A histogram with multiple peaks, like the one seen here, is referred to as multimodal. So understanding whether your data are multimodal can be really important because it basically renders the average as a useless summary measure. So the average here would fall between the two peaks where there's actually the smallest amount of data. And many times when you see multimodal data, it means there's some underlying variable that explains the two distributions. For example, if this was, if we were looking at maybe blood pressure and this is what it looked like, perhaps we have two distributions of people. We have some healthy people and some sick people. So the healthy people have the lower blood pressure values and the sick people have higher blood pressure values. And so when we're plotting them all together, we're seeing, this kind of two peaks in the data, the peak for the people that are healthy and the peak for the people that are sick. And so if we were just to give an overall average, it wouldn't really represent the people that we're actually measuring here. And so being able to understand that structure and see what that data actually looked like can really help reveal things about the data. So this distribution here is right skewed. That means that the right tail there is stretched out and the mode or the peak is going to be to the left. And so in a right skewed distribution, the mean and the median are no longer going to be the same. And being able to, and they're not going to be the same as the mode either, like they were in this symmetric distribution. So being able to see the data like this can be really important. If you were just told the mean, but the data were actually very skewed, you really couldn't get a real sense of that distribution or that shape. So for example, hemoglobin A1C might be right skewed. So you might have many patients in a study that have a normal range, and so they're over there in the peak area. But maybe you have some very sick patients that have much higher values, causing that tail to stretch out. And understanding that distribution can be really important because it can really help you to be able to understand the population and the people that are being measured in the study. Okay, this graph represents a left skewed distribution. And so here the tail is to the left with the peak or the mode to the right. And again, the mean and median are no longer going to be the same, with the mean now falling to the left of the mode or to the left of that peak, and the median falling somewhere between the mean and the mode. So as an example, the age of death in the United States might be a left skewed distribution. So most people die at an old age, and so they would be over in that peak area. But some people die very young, and so that would skew the data or pull it down into that left tail. So here's another example of a symmetric distribution, but this one now is called a uniform distribution. So that means that all the values are about equally likely. And this is another one that you might see out there in the medical literature. And that can be important too, so you can kind of get an idea of, either side of the distribution are just as likely as people being in the middle. Okay, so now let's talk about the pitfalls. There are a number of pitfalls that you want to look out for when you're evaluating a histogram. So when you see a graph like this in the medical literature, these are the types of things you want to be thinking about. The first is the number of bins that were chosen. So the analyst decides how many bins to use when they're plotting a histogram, and this is subjective, and it can influence how the data look. For example, here's a histogram that has 7 bins, and so you can tell it has 7 bins because there are 1, 2, 3, 4, 5, 6, 7 little bars there. And this is that same data, but now the data are represented with 30 bins. And so those two distributions look pretty different between these two, and that's because of the bin choice. And so by just using 7, we were kind of masking what this distribution really looks like. The second thing to keep in mind is the scale. So recall from the previous section, we talked about the key things that make statistical graphics that are important to remember for statistical graphics, and one of them is that it's properly scaled. Okay, so recall that the x-axis here is the variable's value, and the y-axis is often the frequency. It's possible to stretch that y-axis out, giving a very different looking picture. So here's that same data with that y-axis stretched out. And it's also important to take note of what is actually on the y-axis. So sometimes it's frequency, but it can also be relative frequency or percent, or it could be something totally different. So this will be labeled in the literature, and you want to be pretty cognizant to know, is this the percent or is it the count itself, so that you can get an idea of what's actually being measured. Okay, so let's look at an example from the literature. So this is a study, air quality related health impacts from climate change and from adaptation of cooling demands for buildings in the eastern United States. So this study is examining climate change and cooling demand in buildings, and this histogram looks at average hourly temperatures over the month of July. So the red here represents simulated data from the mid-century, and the green represents data from present day. And this is an example of an overlaid histogram. So it's overlaid so that you can compare the distribution of these two groups. And so we can learn a couple things about this graph. The most important piece of information that this graph is trying to convey is that the distribution of the average hourly temperature in mid-century is greater than those in the present day. And you can find this study in PLOS Medicine if you're interested in reading more about it.